All right, let's get started. So, we'll begin the class by seeing the reduction of factoring to order finding. And in fact, as we have discussed before, more generally, period finding or order finding implies a break not only to factoring but also to discrete log. So, let's just recollect what is the um, how to express the discrete log problem as a period finding problem. Okay, so recall the discrete log problem. You are given a group G, capital G, and small g is a generator in this group. Okay, and we are given some h which is g to the a mod p. Okay, and what we want is to find a. Okay, so in order to use the period finding problem to capture this problem, what we could do is we could define f of x y as g to the x h to the minus y. So, this ends up being g to the x minus a y, right. And you can now see that f of x plus a y plus 1 is going to be g to the x plus a h to the minus y minus 1, right, which is g to the x plus a minus a y minus a, which is the same thing as g to the x minus a y. Okay, so, we can see that the period is A1. All right. Okay, so next we want to look at factoring itself. Okay, so here in general the factoring problem is that you are given an integer which is a product of prime powers. For simplicity, we have been looking at the case where it is just a product of two odd primes. Okay, so here of course you have n which is the product of two odd primes p and q which you want to find. Okay, and what we want to reduce this to is the order finding problem. So, what is the order finding problem? Well, the inputs are integers x and n. Okay. So, for order finding, the input are integers x and n such that GCD of x and n is 1. Okay. And the output is the smallest r such that x to the r is congruent to 1 mod n. Yeah. So, this is as the name suggests. So, you're given some input and you want to find its order in the group. Okay. So, what we said is that given an algorithm that will solve the order finding problem, we can factor n, and note that this part will be classical. Okay, so if we can find the order, then the reduction from factoring to order finding is classical. Okay, so let's prove this. Okay, so claim factoring reduces to order finding. Okay. So, in order to prove this, we will show some lemmas. And in particular, we take this intermediate step. So, we first reduce factoring to computing a non-trivial square root of 1 mod n. Okay. So, let us first see that. So, here is a lemma. So, given n and x such that x is a non-trivial square root of 1 mod n, we can find factors of n. Now, note that non-trivial square root of 1 mod n means what? So, it means that well x square is congruent to 1 mod n, but x is not equal to plus minus 1 mod n, right. So, I mean a square root of 1 mod n, the trivial ones are plus 1 and minus 1. So, it is not that. Okay, good. So, let us prove this lemma. So, let us prove this lemma. Okay, so the proof is really easy. So, we have that x square is congruent to 1 mod n. So, this in turn implies that x square minus 1 is 0 mod n, which means that x plus 1, x minus 1 is 0 mod n, but we know that x is a non-trivial square root, right. So, x is not plus minus 1 mod n, right. Hence, x lies between n minus 1 and 1. So, GCD x minus 1 n or GCD x plus 1 n give a non-trivial factor of n. Okay. And why is this procedure efficient? Because we are just computing GCD and we know how to do that using Euclid's algorithm. Okay, so let us now look at another lemma. This new lemma that we will show will come in handy in the future. So, for now we will just state it. Let P be an odd prime and x is uniformly chosen in ZP star. Okay, so that is in the set 1 to p minus 1. Okay. Then the claim is that order x is even with probability at least 1/2. All right. So, let us prove this. The proof again will follow in quite a simple way just by using Fermat's little theorem. Okay. So, by Fermat's little theorem, we know that x to the p minus 1 is congruent to 1 mod p. Okay. And moreover, in ZP star, as we know, this is a cyclic group with a generator G. So, we can write x as G to the k for some k. Okay. And now moreover, because we chose x uniformly, so k will be even and odd with equal probability. Okay, so probability that k is odd is half. Now assume that k is odd. Then what did we get? We got that x to the order x, let us call it r. Okay. So, let r denote the order of x. Okay. So, we know that x to the r is congruent to 1 mod p, okay, which means that g to the kr is congruent to 1 mod p. Okay. And note that this implies that p minus 1 divides kr, right, because g to the p minus 1 is 1 mod p, and moreover p minus 1 is the order of g. Okay. So, this implies this, and now we assumed that k is odd, right, but p minus 1 is even. So, this implies that r is even. Okay. So, we get our claim. So, the only thing that we assumed is that k is odd, and this happens with probability half. So, therefore, we get our claim. Okay. Good. So, now let's prove the main lemma that we need here for the reduction to work. Okay. So, recall that n is p times q, okay, and let us say that p and q are odd primes. Let x be taken uniformly from Zn star. Now, how many elements are there in Zn star? Phi of n, right. So, that is Euler's function. So, anyway, so we are choosing x randomly from Zn star. If GCD of x and n is 1, then with probability at least 3/8, we get that order of x is even, okay, and x to the r over 2 is not congruent to plus minus 1 mod n. Now, note that what this lemma is really saying is that I am recovering a non-trivial square root of 1 mod n. Okay. Why is that? Because we have that x to the r is 1 mod n, right. So, x to the r by 2 the whole squared is 1 mod n, right, and we are saying that x to the r over 2 is not plus minus 1 mod n. So, that means that this is a non-trivial square root of 1. Mod n, right, and this is what we wanted. Okay. So, let us prove this lemma. Okay. So, first we apply the Chinese remainder theorem. Okay, so what the Chinese remainder theorem says is that Zn star is isomorphic to Zp star cross Zq star. So, in turn this means that sampling an x randomly from Zn star is equivalent to sampling 2 elements randomly from Zp star and Zq star. Okay. So, we are going to think of these 2 elements as x1 and x2. Okay. So, we will sample x1 randomly from Zp star, x2 randomly from Zq star, and we will denote each of their orders by R1 and R2 respectively. Okay. So, let me write all this down. Okay. So, choosing x randomly in Zn star is equivalent to choosing x1 in Zp star and x2 in Zq star. Okay. This is just by CRT, and as I already said, I am going to let R1 denote the order of x1 and R2 denote the order of x2. Okay, so now what was our previous lemma? Let's look at our previous lemma. Our previous lemma says that if P is an odd prime and I choose x randomly from Zp star, then the order of x is even with probability at least a half. Okay. So, let us use that. So, now we are choosing x1 and x2 randomly from Zp star, Zq star. So, we can apply this lemma. Okay. So, note that by previous lemma, since x1 and x2 are chosen randomly and P and Q are odd primes, right. We have that probability that Ri is even is greater than half. This is for I in 1, 2. Okay. Therefore, the probability that R1 and R2 are both odd, this happens with probability less than 1/4, which in turn implies that the probability that R1 or R2 are even is even. This happens with probability at least 3/4, and note that R is even when R1 or R2 are even. R1 or R2 is even. Okay. So, the probability that R is even, this is greater than equal to 3/4. Alright, so good. So, if it is even, then that means that I can think of x to the r over 2 if r is even. So, now I need to think about the probability that this is a trivial or a non-trivial square root of 1. Okay. So, this is just a simple argument. So, now since r is even, okay, x to the r over 2 can be considered. Consider x to the r over 2. Okay. So, x to the r over 2 the whole squared is obviously congruent to 1 mod n. Okay. This is just by definition of the order of x. Okay. So, x to the r over 2 is a square root of 1 mod n. Yeah. Now, what are the square roots of 1 mod n? So, again by Chinese remainder theorem, the only square roots of 1 mod n are 1 1 minus 1 minus 1, right, 1 minus 1 and minus 1 1. Okay. So, there are 4 square roots of 1 mod n by CRT. Okay. So, if you were choosing between them uniformly, the probability that you get a non-trivial one is a half. Okay. So, probability that x to the r by 2 is not congruent to plus minus 1 mod n, this is at least a half. So, actually here note that this is just a this is an inequality, because we know that r is the order of x. Okay. So, x to the r over 2 cannot actually be equal to 1. This would contradict r being the order of x. Okay. So, x to the r over 2 could be minus 1, alright. So, anyway, so this is the proof. So, this gives us an algorithm for factoring. How? Because we showed that factoring reduces to finding a non-trivial square root, and then we showed that finding the order suffices to find a non-trivial square root with good probability, and as usual you can repeat and so on. However, I want you to look at this lemma again and tell me, forget the proof of the lemma, just look at the lemma and tell me whether you see any problem in using this lemma. So, why are we doing this, right? So, we are trying to come up with an algorithm for factoring, right. So, we will finally, let us say that we have a box that solves the order finding problem for us, right. What do we need to give this order finding box? Some element x, right, so that it can find its order, and we need to use that order finding box to find a non-trivial square root of 1, and then use that in turn to find the factor of capital N. Do you see any problems in what we have written so far? No, that so the probability being less than half or whatever is not a problem. These constants, we always ignore them. So, at this moment we do not worry about efficiency, like how many times do I have to repeat and so on. So, we are really on the edge of feasibility. We do not care at all about efficiency. No, the problem is actually this. Can you tell me why this highlighted part is a problem? It's because if my goal is to factor n, right, then how do I sample x from Zn star? So, Zn star has order phi of n, right, and if I want to sample uniformly from that, then this is a problem, because if you remember, phi of n is p minus 1 q minus 1, right. So, I do not know what is phi of n. If I knew phi of n, then I could knowing phi of n is I know it when I know the factors of n, right. So, how will I sample this is a problem. So, actually this is why, as I have said before, when we finally use we use the algorithm for period finding, right, we will not be able to really sample from the right set. So, our order finding algorithm, right, our order finding algorithm is going to actually find the order. So, let's think of our function f as let's think of our function f of x, or let me put x in the subscript. So, fx of a as x to the a mod n, right. Okay. So, I do not really know how to pick x from the right set. So, basically I am going to use an upper bound, okay, and this is going to lead to complications in the analysis of the algorithm, which can all be handled. But I just wanted to point out that you know, here, so you have to be careful, right. So, here we just very coolly said let us sample this, but you know, this could be a problem in itself. So, just wanted to point that out. All right, any questions?